Good afternoon, everyone. I am Jake. I'm here to talk about 3 libraries that we're working on at Cash App. Redwood and Zipline are the 2 libraries, and Treehouse is sort of one that's the combination of both. So Redwood is an attempt to be a multi-platform UI library. Zipline is also multi-platform JavaScript engine. And then Treehouse is the combination of the 2. So we're going to step through these libraries individually and sort of build up what they do and how they combine. Redwood initially got its start in this thing called Form Blocker. It's like an evolution of that. And the problem that it's trying to solve is that your designers are going off and crafting these designs, and then engineers from each platform will go and interpret that and build an associated native UI for the app. And so this works, but it's a very common source of interpretation differences as to what the designer was trying to convey is supposed to happen. And then obviously, over time, as the design changes, it's really hard to track which platform has caught up with whatever the latest revision is. And so Redwood and Form Blocker before it are this effort to programmatically encode parts of your design system so that you can do code generation based off of that and use the safety of a compiled language to enforce a bunch of these things that your designers want to expose in the UI. So we start with this schema that we'll look at in a section and a second, and we code generate widget interfaces from them. So the code generation in and of itself is not particularly a novel thing. I think a bunch of people have done code generation from design system stuff, especially around colors and icons. You see that a lot. We wanted to take this a little farther with actually what widgets are sort of the core ones that make up your app. So these are your like app specific buttons and the 3 styles that your app will display that button in. But then, so the thing that we do a little bit differently is rather than code generating Kotlin for Android, Swift for iOS, and JavaScript or TypeScript for the web, we're just going to generate Kotlin and use Kotlin multi-platform to compile that to each platform. Now, that in and of itself turns out to be not that useful. You still can get utility out of it. So the origins of this, the form blocker that I mentioned, we would basically have protos come down from the server, and then we would use those to basically assemble the UI that was common across all of our platforms. But if you start thinking a little bit farther or further about what you can do with this, if you have a common set of interfaces that represent your UI that is in Kotlin multi-platform, well, then you could probably do some sort of business logic that's also in Kotlin multi-platform and compiles to each platform. And so the way that we actually do this is we're using compose. And the key here is we're using compose, not compose UI. We're using the core of compose so that you're still writing composables and all the state management stuff, which we'll see in a second. But the nodes that we target that compose is interacting with is actually these interfaces which are wrapping the native UI toolkit of each platform. All right, so the schema, let's look at a schema, and we're going to kind of build up a little app here. The schema is actually itself Kotlin solely, well, for a few reasons, but it's just a DSL. We never use these types directly. It's just a way to convey to the code generator what the structure of your widgets are. So here we're just building a column that can contain children, and we have a text input, which is like an edit text or whatever. Hint. Can obviously have the text that the user entered, and then it has an event. Great thing about using Kotlin for this DSL is you get all of the things that the IDE has. So it doesn't make much sense to add a birthday to a column, but if you want to add a birthday and you want to use a date, well, the IDE is going to prompt you and say, you need to import libraries. And so any libraries that you're using, or like if you're using protos or something, you can use them in this schema. And then those will wind up in the generated code. So there's 3 basic things you can do, which I sort of covered. You can have a property, which is something that gets set on a view. You can have children. You can have groups of children. You can actually have multiple groups of children. So if you have a widget that has 2 sort of slots or areas that children can go into, you can have as many as you want. And then there's events which are fired. So this would be your button click, your text entered, your touch, whatever. And so one other thing I want to mention about the schema is that you are building this from the ground up yourself to be specific to your app. This is not a thing that's like turnkey that you drop in and there's an entire widget set. So this is an example from one of Google's Compose UI things. If you wanted to build the widget set that would allow you to make this, you could go very granular, build up rows and columns, have real fine-grained primitives like text and image, and then in the Compose code, you composite that together and produce this layout. Or you could go the opposite way and go very coarse-grained and a more semantic representation of what this is. So a contact item, and then when you use this around your app, you know that it's always going to be bound to the layout that is appropriate for this part of your design. And so which one of these is right? Well, I don't know. That's specific to your app. And it may not be one of these two. It could be something in between or something totally different. This is actually one of the hardest things about using the library is coming up with the right level of abstraction for your own widgets. From this schema, we generate the two things, composables and widget interfaces. The composables look almost exactly identical to what's in your schema. So we're generating these composable functions that look like ones you would get from Compose UI, but these are based on the widgets that you define and critically not targeting Compose UI. With these, then, you can build normal-looking compose. So you're doing state management, you're building, you're composing these together. I try not to say compose for multiple things. You're composing them together to build the screens of your app. You're creating the interaction logic. And because this is Kotlin, that gets compiled to every platform. And then what it interacts with are these widget interfaces that are also generated from the schema. Again, they look very similar, and all the things that you write in your schema get contained within these set of generated interfaces. So some of how it works with binding to the native UI toolkit, all these interfaces extend from one called widget, and they basically all are going to hold on to the platform-specific representation of that widget. We're going to look at writing an implementation of one of these in a second. So for the column, if we're writing, Android developer, obviously, and if we're writing this for I don't know, do we call it legacy, the classic Android View toolkit? You're just going to implement this interface, and Kotlin is going to force you to override any functions or properties that are defined. And so if we're going to do this for a column for the old view system, that would probably be wrapped around a linear layout, which we'll take and we'll expose as that value property, which is the native representation of this. And then we override whatever we have to override. So in this case, it just holds children, and there's a little helper in the library for exposing children. So that's great. That's how we bind. The other ones are a little bit more complicated. We'll see a couple more. But the way that there's a second thing that we actually generate, which is an interface that's a factory of all the possible widgets. And so this is the mechanism by which the library can create these instances and assemble them into the tree that's going to be the actual native UI. So for our case, we just have done the column. We implement the interface, take a context, and for our column, we expose our type. And so we would do this for all the rest, button, and I forget what the other ones are. All right, so that's the composables and the widget interfaces. How do they sort of connect together to render platform native UI? I'm going to take a brief detour. This is actually Compose UI. And what I want to look at is how Compose UI executes and builds like a Compose UI, how it renders and builds this tree. So we don't have to care about any of the arguments, any of the modifiers, all that stuff. Really all we care about are the core composables that are going to produce these nodes. And so there's always a root that Compose is inserting these nodes into. And what happens is as there's also a pointer to like the current node that's being operated on. So as your function is being executed normally, if it happens to create a node, in Compose UI they're called layout nodes, then it gets added to the current node that we're pointing at. So we're adding a row, then we go into its children, so we're going to change the current one to be the row, and this process just repeats over and over again. We execute through all of them, and we build up this nice little tree. You don't build the tree. You're writing this, nice declarative, sort of more semantic composables, but the tree is being built behind the scenes. And what happens is this is very much like a classic UI toolkit thing, but it's entirely behind the scenes. So now there's like a layout pass will happen. It will traverse this tree and do a layout pass. And then if it wants to draw, render the pixels, it will traverse this tree and do right to a canvas or whatever. So I want to do that same exercise really quickly, but instead of Compose UI, we're going to look at what Redwood does. So when the root is created, with Compose UI, the layout node is like the primitive, but we have something in the native UI toolkit. So we're also going to hold on to a frame layout, in this case for the view system. And then as that compose code is executing, and that tree is being built, we're calling the factory and creating these nodes, which themselves hold on to platform-specific representations of your UI. And so we're building a parallel tree of these lightweight wrappers, and then also the native UI toolkit, which is attached to, in this case, an activity or whatever. And that's what allows us to build. And actually, these mappings, I didn't do it on this slide, but these mappings don't have to be one-to-one. So for the implementation of that contact item, where it was the high-level contact item that we would put in the schema, that might itself be a relative layout that has multiple children in it. And so one of these nodes in the native tree could actually be like a couple actual views. And it would only map to a single sort of semantic one in the compose tree. And then we just do the same trick on every platform. So your compose code's running on iOS, well, just build the iOS native tree by using those lightweight wrappers that your iOS team has built. You want to do it on the web, you build a DOM tree using lightweight wrappers. And so by encoding our design system in both these interfaces that are implemented, trivial to wrap around native components, and the code generation of the composables, which allows us to write normal looking, what people think of Compose UI code, except targeting our design systems components rather than Compose UI's more general purpose ones. We can target the existing UI toolkit of whatever platform we want to support. So real quick, the implementation of these composable functions, I just want to show, this is like the connecting bits. We have like a custom function. There's compose node is the normal one. But basically all this is doing is it's taking an instance of that factory, and its goal is to produce an instance of the interface that corresponds to the current node. And so we use a function reference, we pass the compose. So anytime compose sees this function as it's executing and deems that it has to create a node, it will essentially call that factory function for us. It'll be returning an implementation of that interface, and that wraps the native UI toolkit. This update lambda is another compose thing. We basically bind every argument to the composable to each of the functions that are in the interface. And again, when compose sees that one of these arguments has changed, it's going to go and call basically the lambda here that we've defined, which is then going to call the function on the interface. So if only this text has changed, only the text function will be called. Just to belabor that point, so if we have this node and it's being bound to some property and some data class, if compose recomposes, sees that value has changed, it's going to call our text function, and then in turn we will set the text property of Android's native text view. Same thing works for UIKit and HTML or whatever UI toolkit you're targeting. So I said that Redwood basically ships with nothing. You build up everything yourself. That was a little bit of a lie. We actually ship with a layout engine, a Flexbox-like layout engine. Doesn't put any pixels on the screen, so you're not, we don't have to be opinionated in any way. but it's really annoying to build up simple layout primitives when all you want to do is start putting actual pixels on the screen. And so we provide this for you. All right, I want to look at actually the first sample that's in the repository and how we build it up. And we'll actually see it, well, we'll see screenshots of it executing, and we won't see one executing until later. So this is the entire schema. This is a counter, really simple. So all we need is text and a button that we can click. From this, with the generated code, we do, pretty much the most basic compose that you can write. And remember, we're targeting our generated code, not compose UI. So even though the names look similar, this is our stuff. We have the layout that I talked about from Redwood that we ship. And then we just have normal compose state management that you have to learn. There's, you can do the mutable states, you can do effects, you can do, there's keys, you could do all the primitive composey stuff is still here. So this gets compiled to all of our platforms. In this case, this sample runs on basically every platform we support. So that's going to be Android, the JVM, iOS, JavaScript. And you could do Kotlin native for desktop or whatever. I guess we actually don't do that one. So we bind these widgets. Here's another example of just how kind of simple these are. They're just really basic. You're usually mapping, trivially mapping these things to platform native properties. So this is the one thing you do. You also do the factory. This is sort of the bulk of your responsibility. But then we also have to set it up. So this is a bit what the setup code looks like. One-time setup. So it's a little verbose. That's fine because we only write it once. We have a scope in which compose is going to run and where our effects are launched into. We have the container into which the nodes that Redwood creates, where they're going to be inserted. So in this case, this is in an activity in this sample. We just take the root content view. Redwood is not an all-or-nothing framework. We don't need to take over the entirety of the screen. You can take over just a tiny little frame layout or linear layout anywhere in your layout. You even have multiple running with different view groups, which we also do. And then the last thing is just tell it about the factories. So we have the one on top, which is the one that we would have written that creates our instance of text. And then we also, for the layout that we ship to you, we have implementations for every reasonable UI toolkit. So in this case, we're still doing the classic Android views. And then we just give it our composable. So it's a set content method, very similar to what you would see with compose UI. And that's our composable that we saw before. And so now we run this app, and we have a nice view tree, a native view tree on Android running our compose code. But we're not stuck. We're not building this library into future obsolescence by only targeting the legacy Android or the classic Android toolkit. If you want to do compose UI, you can do compose UI. This is an implementation of the text. We also have one on the button. Setup looks a little bit different. We still are creating the factories, but now with the different, the compose UI specific ones. And then the outer part of this is compose UI. So that's the set content on an activity. We have our theme. We made a little material theme. And then this Redwood content is a bit crazy to think about, but it is a compose UI specific function that itself runs another instance of compose to run the Redwood compose inside of that. And so when our counter is running inside here, the Redwood content lambda is basically going to be creating those compose UI, I don't know what you call them, instances or whatever, and attaching them to the enclosing compose UI rendering. All that to say, you can do compose UI with Redwood. It really should be any UI toolkit that you want to be able to target, you should be able to target. Hey, now that we have compose UI running, why don't we run it on the desktop? So the bare minimum boilerplate for setting up compose desktop, using the same implementations, done. Our app now runs on desktop. Targeting the web, this is written in Kotlin. You could write this in JavaScript, TypeScript. I wouldn't recommend it. It's a lot easier to write this in Kotlin, but the DOM nodes that you're talking to, hopefully we're going to put a React sample up soon where we're targeting like React. But since this is the simplest sample, we just target the DOM nodes directly from Kotlin. And now our app runs in the browser, and you can see, we're using normal HTML elements. And then finally, we want to run on iOS. So again, this is iOS. The implementations are in Kotlin. So we're implementing the, we're still targeting UIKit, but we're implementing the interfaces in Kotlin. You can do this in Swift. We do this in Swift, and one of the other samples is implemented with its implementations in Swift. But since this one's the most basic, we stuck with Kotlin. And then there you go, running on iOS, and you can see native UIKit views. Same composable, powering this, compiling to every platform, and then the enforcement of the schema is basically enforcing that we have the same widget set available on every platform, and our responsibility is just to figure out how to map that to native UI. Redwood takes care of the rest. Okay, Redwood, the key really is, you have one design system. The upfront cost of Redwood is actually rather high. But if you have this design system established and you can build out these schemas in a way that all the platforms agree with, you can target multiple platforms while still being able to write a single set of composables that run on each platform. Okay, we're going to left turn slightly, but I promise we'll make our way back. Zipline is a thing that we've been building and talking about for about 8 years now. It is a JavaScript engine, runs on Android, iOS, the JVM, other Kotlin native targets like desktop. And there's really two main use cases for it, which would be if you had some plugins that you didn't trust and wanted to run in sort of a sandbox environment, or what we use it for, which is we want to update code in the wild faster than normal release process of app stores to change some behavior for our customers. I have a motivating example. This is a real motivating example of why we started doing this, and then we'll get to sort of how we realized that actually we could do a lot more. So this is Cash App. Cash App is primarily US-based for now, and this is the United States. We have 50 states, and you think to just operate in the United States, it'd be easy. You just get one government's approval to send money around. Actually, you have to get approval from all 50 states. And what's unfortunate about that is the requirements differ for every state. So what Florida wants is different than New York or California, and you have to comply with these. So here I've sent a payment to my friend Alec, but if I instead sent a payment to like the American Red Cross, Florida can come and just say, that actually is a nonprofit, and you can't say payment, you have to say donated. And by the way, you have 7 days to comply, or we revoke your money transfer license. So 7 days is, not too terrible. So yeah, they want us to put donation here. 7 days is not too terrible. On the web, obviously, this is like 1 day turnaround, no problem, change the string. Android, we can land this today, but then we have to go through the release process. Now we have, QA and stuff. Do we roll it out? Do we go straight to 100? iOS, similar. It used to be worse. Actually, sometimes now it's faster, although Apple, if you really, really need to go fast, you can just throw money at them, and they will do an expedited review, which is awesome. We don't have that on Android. So what we want to do, and what we've changed to do instead historically was, well, we want to be able to drive this from the server, update this from the server. And so the mechanism we chose after looking at a bunch of different ways to do this was we're just going to run a JavaScript engine on the clients. So we're going to take the payment in, and we'll have the rendered strings come out. And that way, this logic of whether or not we need to say, is it a payment or a donation, can live inside the JavaScript and get updated. So we do two things with the JavaScript. We package it in the binary when we ship it to the App Store or Google Play. This is for the offline case, the first run case, you're on the tram underground case, when you don't have connectivity. We want the app to still work and the user to not know that there's a JavaScript engine. But then when this occurs, and it at the time was occurring multiple times a year, we can now update that file on the server and have it be distributed down to all of the clients the next time they have connectivity. So that's the motivating case. The way that Zipline, so we used to just do like JavaScript engine, ugly, stringly typed APIs talking to it. Zipline is the evolution of that. And so what we do is if you had this code, this logic in your app natively, you'd probably just have a class that takes the payment, returns a string. So what we're going to do is to make this updatable and run on Zipline, we're going to extract out an interface. So now we make our code that's interacting with this, unaware of how the implementation is. And what we want to do is take that implementation and move it into the JavaScript engine. We used to write an ugly implementation of this class doing the stringly type stuff and dealing with JavaScript and whatever. Zipline, however, takes this farther, where what you do is you actually put a marker interface on your annotation, which is going to be a hook for a compiler plugin that Zipline has and runs. We'll look at what that does in a second. What this allows us to do is move the implementation of this into JavaScript, which is what the top is meant to represent. And so we can have our JavaScript code run and then expose the implementation of that interface to Zipline. And then in the host side, the Android app or the iOS app, we can then take that interface implementation without knowing anything about it, without even knowing that it was, is talking across a JavaScript bridge. And then we interact with it like it's a normal interface, any other interface. But the key is that now we can take that implementation, throw it away, and load a new one from the server. And what's cool is that Zipline itself, the host side, so we call this guest and host to because other terms are too confusing or overloaded. So the guest side is the JavaScript. The host side is what is in your Android or iOS app. We used to do this just for Android, and iOS did their own thing with JavaScript core. Zipline itself is a Kotlin multi-platform library that also targets Kotlin native. And so that code on the bottom, the code that actually interacts with the Zipline instance and figures out how to get and set all these services, that can be multi-platform too and compiled to your iOS app and shared. This is also a bidirectional system. So right now the implementation of an interface is running in JavaScript and we're consuming it from the host. We can have an implementation of an interface on the host, such as get the location of the current device and expose that into the JavaScript so that it can do the inverse, which is to take the implementation of that interface. And you just have to get the ordering correct. So the host binds its stuff, then we load the JavaScript from the server. The JavaScript will run, so it will take the interface from a host. It will bind its instance out into the bridge, and then we can take that on the host side. The types that we support, or rather both types and the mechanisms of functions that we support, you can do synchronous, which is what I've been showing. We support coroutines, so suspend functions, and this is not like you're running a synchronous function in JavaScript. You have to remember, you're running Kotlin compiled to JavaScript, so this is a Kotlin coroutines code that can be doing database lookups, networking, whatever. So it's truly async that's running in the JavaScript, and we take care of holding on to the callback and resuming your function on the host side once the JavaScript side has returned a value. You can do flows. We have special support for flow. And basically what happens here is when you start collecting on the host side, we start collecting on the JavaScript side, and then every value that comes out, we send across the bridge. Stateflow also works, and these don't have to be, this is, again, bidirectional, so you can send a flow into the JavaScript or you can take a flow out, doesn't matter. And then any type, absolutely any type can be sent with a caveat that we need a way to get that type into JavaScript. And so how do we do that? Well, we're going to look at what the compiler plugin actually does when it runs. It's going to put it puts an implementation of an object in every one of your services, and this basically is going to generate code that knows how to interact with the Zipline stuff. So when it's called, it gets this thing called a handler, which is kind of a wrapper around the current engine. And then as the functions are called, we pass it into the handler, and we cast the right type back out. And what the implementation of this is doing with these types, well, it's serializing it. So we need like a multi-platform way to be able to serialize arbitrary types. Well, there happens to be a nice JetBrains library for that. This entire system revolves around using Kotlin X serialization. And basically, these types are, all you need is either to have them be marked as @serializable, or if it's an arbitrary type that you get from a library or something, or that you don't control, you can register custom serializers with the Zipline instance. So this is built on a JavaScript engine called QuickJS. It's about 1.5 meg. And I just want to talk about one interesting thing about how it works, which is it's a two-step process. So we have to be an interpreter to run on Android or iOS. So what it does is it compiles it to a compact bytecode ahead of time. This is a text representation of the bytecode. The actual bytecode is binary. And then that is what's used. That is what it's interpreted to produce the result. And so every time we load JS, we have to do this compile step, and it seems like something that is like a waste when you push out a new JavaScript, that you're forcing everyone's phones to do this compilation step. When instead, what we want is to be able to do it once on the server and ship that to the client. And so that's actually what we do with Zipline. Zipline supports loading this compact bytecode format, which doesn't need to be parsed and lexed and all the stuff that JavaScript compilation has to do. Instead, it can just immediately go to executing the function. But we have to remember, JavaScript is not our original source here, right? This is a JavaScript engine, but Kotlin is the source of the code. And what's unfortunate is, Zipline doesn't know that. And so in the generated bytecode, there's references to the JavaScript, the intermediate JavaScript file. And so that's unfortunate, because if you get a crash or whatever, it shows up in stack traces, and you're like, I don't know what, this is like an extremely trivial example, but when you run through Webpack, it puts everything on the first line. It's like one line of 50,000 characters, so every stack trace is like, oh, it was line 1. You're like, oh, great. However, Kotlin, thankfully, or rather JavaScript, thankfully, has this source map spec, and Kotlin utilizes that. It generates this file which says, whenever you see JavaScript line 1 at column 40,000, actually that's line 600 from the Kotlin file. And so what we're able to do with Zipline is we actually pre-process the bytecode and rewrite all of the references to where the code came from to be the Kotlin references. And this is great. So what this means is that when your code crashes, which it inevitably will do, you wind up with references to your Kotlin. And what's also interesting about this is a Zipline crash. One of the things we do, at least only on Android or the JVM, is we actually mix and match the stack trace until you called into the JavaScript engine, and then there's the JavaScript stack trace is actually merged together. So you get this unified call stack. Again, just trying to make the JavaScript engine as opaque as possible. You're writing Kotlin on the host side, you're writing Kotlin on the guest side. We don't want you to know that there's a JavaScript engine in between. We just want you to leverage the mechanism that is updatable code. So JavaScript is great. Support in Kotlin is fine. They target what is now an 8-year-old version of the JavaScript spec, which is not great. There's maybe going to be some updates to that, but what we really want is probably to be WebAssembly. And what's great about Zipline is that we can't just change the engine from JavaScript to WebAssembly without you knowing, but we kind of can. It'll be like a version 2, and you have to be aware of what's going on, because now your guest code has to be compiled to WebAssembly, not JavaScript. But otherwise, the interaction and how it works is not going to change. And because the unique requirements of having to be an interpreter, and Kotlin also has some really new requirements in what capabilities of WebAssembly are supported. There's not really a viable WebAssembly engine right now, so there's 2 that we're tracking. Hopefully next year, we think it'll actually be viable. Okay. So that seemed like a little bit of a detour. Treehouse, so that's Zipline, Redwood, multi-platform UI toolkit targeting thing. Maybe you can see where we're going. Treehouse is the idea that we can combine these two things and basically get updatable presenter logic. This is our counter that targeted the Android the classic Android UI toolkit. There's two main things going on here. We have the interaction with the host UI toolkit. So this is the root view that we're putting things into and the set of widget factories that produce our implementations of our widgets. And then we have the compose side, which is purely business logic, and the output of that is interactions with the node tree. It's insertions, removals, or it's changes of properties. So the idea is to take that compose stuff and run it inside the JavaScript engine and have the host application still running all the native UI toolkit stuff. So we can't do this. It's not just that simple. Like, it'd be great if it was just that simple. It's not just that simple because we can't hold the necessary references across this boundary. The compose wants to hold on to these nodes so that it can do things. It can just perform the interactions with them, but also how like the diffing and stuff winds up getting applied. It just doesn't work. We need an indirection. And we know Zipline, what Zipline requires. It basically requires us going through Kotlin X serialization, and so we just have to write a bunch of boilerplate code to map these interactions. I want to insert a button at this node. I want to change text property on this node. We need to write the code that turns that into something that can be serialized across the JavaScript bridge. Similarly for events flowing backwards. Of course, we don't have to write that ourselves because we have this type-safe schema which defines all of the types of widgets and all of the properties and all of the events. So we just code generate those. We code generate those, and then now those are the pieces that we fill in, and this data flow works. So as compose recomposes and is performing these interactions on the tree, insertion, removal, rearranging, setting properties, updating properties. We're essentially recording all of those using this protocol, which is designed to be very compact. Send that across the Zipline bridge, and then we do the inverse on the other side as we unpack that, interpret that, and says, okay, it wants me to insert a button in this, underneath this node, and then we apply that through the same APIs that it otherwise was using when it was all running natively, but now we're doing it by interpreting this protocol rather than compose, driving it directly. And guess what? Now we can throw away our entire presenter logic for a screen, download a new one, and run it. Don't even have to restart the app. So in order to facilitate this, we're going to see an example of this running in a second. But in order to facilitate this, we have to add some data to our schema. We don't want names to matter because names change a lot. So instead, there's basically numbers that have to be applied to everything. Unique numbers for every widget, and these have to be stable forever, basically. So you don't change them. If you throw one away or you want to change a widget, you make a new one with a new number. And that's because we're going to be targeting apps that are in the wild. And so we can't change these numbers because we can't change the code that's running on the user's phone without doing an app update, and that's the whole thing we're trying to avoid. And then it's the same for properties, and it's the same for children. So you just have to give them unique numbers. It's kind of protobuf if you use protobuf. We originally thought we might use protobuf as the schema. So the idea behind Treehouse is basically to package up all of this stuff that is going to be common to trying to pull this off and wrap it up in a nice package. So it will do things like caching the JavaScript or the bytecode. If it's been downloaded, it has like policies for how often it will reload. Just a bunch of convenience APIs about tying Redwood and Zipline together. All right, let's see what a Treehouse demo looks like. So This is a little bit of a different app. This is called Emoji Search. This is the second sample in the Redwood repo. We're running Android, iOS, and web are all running the same version. It's just a simple input field where we're filtering a list of all of the emojis that are available on GitHub. So I'm going to interact with the Android and the web app. I'm not an iOS programmer. The iOS text box ended up underneath the status bar. I cannot figure out how to get it below it, so I can't click on it. We're not going to interact with it, but it will still be useful because you'll see it. It is running, and you'll see it update. So I'm going to go in and I'm going to filter, filter this, look for trees, Treehouse, and we see these emojis on Android and iOS. But I don't know what these emojis mean. I just see the pictures, and so what I want to see is the label. So I'm going to save in the editor. There's a terminal there that's doing JavaScript compilation. And now, this is a video, so I'm not. You'll see that it updates. Our app has updated essentially in like 2.5 seconds or something to now show me the labels of the widgets. The apps update instantly. The web, you have to like manually do a reload. Just because that's how the web works. Every page visit is like a fresh load or whatever it can be. And then this is basically not only a way for us to, try and accomplish that goal where we want to update our customers' apps in the wild with, new potential business logic or whatever, but it's a pretty great development experience as well. I can be prototyping something and actually just run the Android and iOS app side by side and see what it's going to look like on both. All right, so Redwood is the technology that powers multi-platform compose, not compose UI, code generation, targeting whatever UI toolkit you want, usually the native UI toolkit. And we do this because we value the native UI toolkit and the experience that it gives to our customers. We think that's the right choice. If we didn't, compose UI on multi-platform or like a Flutter or whatever is the superior choice for that use case. But we really think that we don't want to abandon our iOS engineers. We don't want to abandon our web engineers. We're not trying to replace them. We're trying to empower them. And so that's how Redwood got started. Zipline, yes, it's a JavaScript engine, but I want you to think about it as a way of just running Kotlin code such that it can be updated out of band or faster than whatever app release cycles that you have. It's totally transparent. You shouldn't have to really know that it's a JavaScript engine. As long as you get the Kotlin serialization of your types, interfaces, and implementations, you really shouldn't know that it's running across that bridge. And then Treehouse is both of these wrapped up together and sort of with all the additional helpers that you need to integrate them together. So I talked about how it handles things can handle things like reloading, caching, all that stuff. So this isn't, hypothetical. We are using this in cache. So this is a picture of a screen on Android and iOS running entirely, well, maybe not entirely, not the navigation bar at the bottom, maybe not the top, but definitely all the tiles and all that stuff. That is all powered by Redwood. And you can kind of look and see what the schema for this probably would be. There's going to be a tile, and the tile probably has a title and a slot for whatever the content is, or maybe there's multiple choices for what the content can be, an image or a graph or whatever. And then on the Android one, you can see more because it's taller. There's row, there'll be a row schema that probably has an icon, primary, secondary text, or whatever. Some of the things that we're doing as an example here, it's utilizing Zipline. So the host app is going to be exposing an HTTP client or an RPC client so we can talk to the server. It needs to talk to persistence to get the values of your balance or whatever. So we have sort of a key value store that returns flows. Navigation, so you click on one of these things, it goes to the host navigation because we don't know if the next screen's going to render with Redwood or the next screen's going to be native UI. Again, this is not meant to be an all or nothing thing. This is not a silver bullet library. It's really meant to tie into your existing applications. And again, the reasons is a lot of this UI we probably share with other parts of the app. And so the implementation of the button certainly is going to be shared the entire app. Maybe not the tiles, but like what that means is that if somebody innocent or unaware of the fact that Redwood exists, they go and change that button, well, that button's going to reflect both in the native UI and also the Redwood UI. They never have to know that this thing is there. Again, one of the things that we think makes Redwood sort of different than, and a reason why we don't have split UI toolkits or anything. And so you can think that now it's easy for our product managers and stuff to run experiments on the screen or whatever. They can literally just land a PR, code gets compiled, deployed to our CDN, change a feature flag, and it's now in the wild. Turnaround time can be under an hour. It's pretty cool. But again, requires a lot of upfront investment. So both of these projects, Redwood and Zipline, are open source libraries. They're available on GitHub. Treehouse is inside the Redwood repo because it is Redwood running on Zipline, so that we keep it all in there. There's not a whole lot of documentation. We'll get there. Zipline's actually we think it's going to be nearing a 1.0 within the next couple of months. It's sort of been stable for a while. Redwood, very new. It'll probably be a while before it's any kind of 1.0, but we are using it in production. We think that it's going to be something that we'll be using for a while, and we have it open source because open source is the best place to work on stuff. And that's all I got. Thank you guys very much.